Anybody have something else that they would like to see? Yes,
Can we do number 4, A and C?
number 4. A and C. Okay. Now, the 6 multiple choice questions on the AP test come from kind of the main concepts. You can usually predict what the free response questions are going to be like. There's going to be a differential equation problem. There's going to be max min, local max min chart kind of stuff. Probably 2 of those because we do so much of that. There's going to be some sort of related rates, maybe. Slope field, well, it'll be differential equation. Then there's going to be some of stuff we haven't learned yet, obviously, like number 1 and 2 that we skipped here. Okay, well, here's the differential equation one that they have you do. Now, they want you to verify this. So, they tell you that your differential equation is y prime equals y minus y squared over x. Well, that's where we did this t-chart business. And they're telling you the solution they think is x over x plus c. So on this side, we need to just plug that in. So we get x over x plus c minus x over x plus c, quantity squared, and then all over x. So there should be some algebra we're going to do to that. On this side, we want y prime. Where are we going to get y prime? Derivative of this. How are you going to do the derivative of this? Calculate, except it's no calculator. So we do the derivative of the top is, it's going to be quotient rule, right? Derivative of the top is 1, bottom left alone. Minus top left alone. What's the derivative of x plus c? Just 1. C is a constant, so the derivative of c is 0. The derivative of x is 1, c is a constant, so it's 0. Okay, all over the bottom square. Now, if you look at this, x plus c, take away x, the x's are going to cancel, and you're just going to have c. So over here we get c over x plus c squared for our y prime. Now that's important because we're going to actually use that later. So we just found our y prime is equal to this. Now that's different, obviously, than our differential equation up here, because remember, in the differential equation, they said this does not apply when x is 0. Okay, clearly if you put x 0 in there, it's undefined, the slope's undefined, but if you look at the slope field, the slope's not undefined at 0, okay? Not everywhere. At 0, 0, it's not. There is a slope. So we're going to use that later on. All right, but right here we got to do some algebra. What can I do to this? Square the top bottom here first. So this would be x squared, and this would be all this squared, okay? So I'll square the top, square the bottom. Now I need to get a common denominator. So I'm going to take this times x plus c. You could do the bow tie thing, but that actually complicates it, I think, in this case. Multiply top, bottom times x plus c. So when I distribute there, I'm going to get x squared plus cx minus this x squared up here. That's going to be nice. Then I'm going to get x plus c quantity squared as my common denominator. Now that's all over x, but what can I do instead of divide by x? Multiply by the reciprocal. So instead of dividing everything by x, I can multiply by the reciprocal out here. Now, some good stuff's going to happen right here because the x squareds are going to 0 out. I got cx on top, I got an x down here, so I can cancel that x. So look what I end up with, c over x plus c squared, which is a match. So there's our verified. Same kind of thing we did when we were doing differential equation. Okay? Verify that it's equal. So you got 2 or probably 3 points in there for your various work. Okay, so that was part A. Now, there's another part of part A though. Part A said show that 0, 0 is what? In a part of every solution. Okay? And what that means is plug it in right here. If you put a 0 in for x, you get what? If you put a 0 in for x, you get 0 over c, which is 0. So any solution you have, in other words, no matter what c is, 0, 0 is going to work. Now that comes into play in part D when it says sketch both branches. Whenever you sketch a solution to this differential equation, you have to have part of the graph go through 0, 0. Because it just said 0, 0 is going to be involved in every solution, no matter what c is. Okay, so that was the importance of what they just told you there in part A. All right. In part B, write an equation of the particular solution that contains a point 1, 2, and find the value of dy dx. Now I know, Alex, you didn't ask about that, but I think maybe some other people do wonder about that. So we're going to put the point 1, 2 into here, right? So we got 2 equals 1 over 1 plus c. So that would mean if I multiply 1 plus c over to this side, I'd have 2 plus 2c equals 1, 2c equals negative 1, c equals negative 1/2, right? Now I'm going pretty quick to this, and I jot some of it down, but you really need to go back and look through. If there's some of this you have questions about, certainly come see me. But all we did is we took our solution, this is our general solution. Now they want the specific, or they called it the particular solution. We want to plug our initial condition in, our 1 and our 2, and we want to work it out and find c. And we get c equals negative 1/2. So if I go to a new page here, so I've now got my equation to be y equals x over x minus 1/2. So this is the solution to my differential equation that we're talking about now. It also said in that part to find the slope of this solution at 0, 0. Now remember what our derivative was? It was c over x plus 2 squared. Right? Remember that from before in part A? So what do I do with that? Put negative 1/2 for the c, and put what in for x? 0, because this is at 0, 0. So x is 0, so we get 2 squared, which is 4. What's negative 1/2 divided by 4? Wait, I did something wrong there. What did I do wrong? Oh, this is, no. It's x plus c. Thank you. Not x plus 2. It's c over x plus c squared. So this should be, okay, now put a 0 here. So this is negative 1/2 over, and this would be 0 minus 1/2. So that'd be negative 1/2 squared is 1/4. So this is negative 1/2 over 1/4, which would be negative 1/2 times 4, which is negative 2. So that means back on this slope field, in the solution that I'm going to be looking for, at 0, 0, I've got a slope of negative 2. So that means back here, come on, slope. I'm going to have a slope of negative 2. That curve is going to be going down. Now, in part C, is that when it asks you to sketch? No. Okay, let me jump ahead to part D. In part D, it's going to say, okay, here at 1, 2, sketch both branches. Well, the one branch is really easy to see. You can just see that it's going to be that. But we know from our work in those earlier parts that there's another branch here. And it's going to come down like that. Because we learned in part A that every solution includes the point 0, 0. Okay, so they were really leading us through that as they went through that problem. Okay, so I jumped ahead a little bit. Okay, now it says write an equation of the vertical and horizontal asymptotes. This is another really key thing where we pull on stuff we've learned before. Okay, the solution equation in part B was y equals, help me out here, it was x over x minus 1/2. Okay, that's our solution that we've just graphed. I've already graphed it in part B. How do you look for a vertical asymptote? Bottom is 0, where the bottom is undefined, right? That's a vertical asymptote. Well, that would be when x equals 1/2. Sure enough, look at here. That's off a little bit. But I've got a vertical asymptote there at 1/2. Now there'd be a lot of different, it depends on C. It depends on what C is. Because you look at these branches, there could be a lot of different vertical asymptotes, right? All right, but this particular one was at 1/2. Right? What about your horizontal asymptotes? Where do you look for one of those? This is one we always struggle with a little bit. Verticals are easy. Where do you look for a horizontal? It's pretty easy to see in my picture, but supposedly we hadn't drawn it yet. No. Horizontal asymptote is what is the graph approaching way, way out in the boondocks, right? Way out here and way out there. It's a limit. A horizontal asymptote is a limit as x approaches infinity. That's what a horizontal asymptote is. It's a limit. Well, sure enough, we have to call on what we've learned about limits. What do we say to do if you want to know what this is doing as x gets really big? High powers, no, not infinity. We can't get on the right of infinity, right? High powers dominate. When x gets really big, the high powers dominate. If you have a billion over a billion minus a half, that's basically a billion over a billion, which is 1. Or we talked about, look at the coefficients on the highest powers, 1 over 1. Okay, that's one way to look at it. We also had L'Hopital's rule. L'Hopital's rule said if you get 0 over 0 or infinity over infinity, you can do what? Continue on by doing what? Derivative of the top, derivative of the bottom. Remember that? That was L'Hopital's rule, f prime over g prime. Derivative of the top, derivative of the bottom. Here, as x gets big, the top's getting big, the bottom's getting big. That's infinity over infinity. We could do L'Hopital's rule. Derivative of the top, 1. Derivative of the bottom, 1. 1 over 1. So, the limit here as x goes to infinity is 1. What we have is a horizontal line at y equals 1. That's our horizontal asymptote. And as you can see from the graph, it certainly is. And do you notice how that did not matter what c was? It did not matter which particular solution we have. And notice from the slope field, the horizontal asymptote's at y equals 1 no matter what. The vertical asymptote would change depending where your points are, right? It would depend on c. This one wouldn't matter. The 1/2 didn't matter, right? Horizontal asymptote is 1. So that's part C. And then we just did part D is the rest. Okay? All right. Any multiple choice ones? This is it. I mean, this is all we'll talk about sample packet 2. If you've got some other questions, we have to do mostly outside of class probably, or we have some work time later on, but we'd like to be finishing up with this. So does anybody have, we could do one more. I want to give you some more time to work on the book assignment here. Okay, nothing, well, we have some work time if you want to ask me, we could, but, okay, so let's go ahead and get your book open, and we're going to be in page 275, roughly there, and for the next 2 days, the idea is let's talk about this stuff that's in the book, have some work time, probably enough to get it done, pretty much. A lot of the people, second block, got the book assignment done, and then that'll free you up for outside of class and continue working on the packet. Now this time would be the third packet, okay, the one I gave you yesterday. Continue working on that. Then also at the end of the period, I'll give you the take-home. And again, the key there is kind of meant to be the take-home thing. So tomorrow during class, when we have some work time, my expectation is you work on the book assignment, you work in the packets, okay, and then you'll arrange for outside of class time to work on the take-home. Okay? I won't do a backpack search or anything, when you come in to see if you've got it, but that's the intent, okay? So we get the book assignment done in class, or pretty much done, then you can work on that tonight, even if you want to, or the packets, but whatever the case may be. For this third packet, you're probably just, we're going to have other stuff going on as we go through it, so you want to work a little bit, let's get some of it done tonight, maybe a little more the next night or whatever, and just kind of get gradually through it. And then middle of next week, we'll be finishing it up and have a fourth one to do right before we do the midterm. Okay, so this section 4.8. Title of this section is Why Continuity Matters. Why continuity matters. So that means why is it important? This means is why is it important that functions are continuous? What does that do? If we know a function is continuous, what does that help us do? Well, we haven't talked a lot about the theory in calculus. These are a couple sections where we get into the theory a little bit. And I told you that no calculator quiz next Tuesday will be about these kind of things, the ideas behind stuff we've done here in chapter 4. All right? So the first piece of theory we're going to talk about here is the extreme value theorem. Which your book refers to in the homework a lot of times as the EVT. The extreme value theorem. Now, I've often told you, hey, on the quiz you can expect questions like this or about this or whatever. Well, on this quiz, I'm going to actually tell you 3 of the questions ahead of time. There will be a question on the quiz next Tuesday that says, state the extreme value theorem. Okay? That exact question will be on the quiz next week. State the extreme value theorem. And here's what I'm going to word it a little differently than what it says in the book. If f is a continuous function over a closed interval a comma b, if f is a continuous function over a closed interval a comma b, then f has both a max and a min value. Okay? Now, that doesn't seem to be anything too earth-shattering, but when we were doing optimization problems, we were looking for a max or looking for a min, it's good to know that one exists. And basically that's what this is. This is called an existence theorem. It just guarantees that if you have a continuous function over a closed interval, then there's going to be both a max and a min value. Okay? Now, something that you got to understand about these if-then kind of statements. In computer math, we talked about this a lot. Okay? And so I'm going to, in geometry, you do some of this. Okay? So think of the extreme value theorem as a promise. All right? If the function's continuous and if you're looking at a closed interval, then you're promised, guaranteed, to have both a max and a min value. That promise cannot be broken. Okay? It's been proven. It's a true statement. Okay? Under what circumstances, if it was possible for that promise to be broken, under what circumstances would that promise be broken? If what happened? Oh, now, okay, there you go, a great example. Horizontal line, is that a continuous function? And let's say you looked at a horizontal line from 2 to 7, and it was at y equals 8, right? Is that a continuous function? Closed interval? Yes. Does it have a max value? What's its max value? 8. What's its min value? 8. So there you go. It has both a max and a min value. There's nothing that says a max and min have to be different, right? It just says a max value would be there's no values greater than that. There's no values greater than 8. And a min value, there's no values littler than that. So it'd be 8. So that would be okay. So the promise wouldn't be broken in that case.
So it can't be a vertical line?
Vertical line is not a function. So that wouldn't break that promise either, because if it's not a continuous function, then or it's not a function even, right? It's not a function, then it doesn't, yes?
Wouldn't a non-continuous function have a max and a min too?
It could. It's possible for a non-continuous or a discontinuous function to have both a max or min, and that's a great, glad you asked that, because that's my point here. Does this theorem say anything about what a not continuous function has as far as a max and a min? This doesn't promise anything about that. And I give the example in computer math. It said, if you get an A in this class, your parents will buy you a, what I said, car. Car. If you get an A in this class, your parents will buy you a car. Right? Maybe I said I was, yes. If you get an A in this class, then I will buy you a car. Purely hypothetical situation. That's why, oh yeah, last period I said iPod. That's probably why I said it, because I couldn't afford the car, so iPod. If you get an A in this class, then I'll buy a car. So let's say I made you that promise. If you get an A in this class, then I will buy you a car. Now, I'm guessing immediately you assume, and you guys in computer math know where I'm going with this, immediately you assume what?
If you don't get A, you won't.
If you don't get the A, you won't get the car. I mean, let's face it, if your parents actually made you that promise, or somebody made you that promise, that's probably what they meant. But that's not what they said. They said, if you get an A, then I will buy you a car, right? What happens if you don't get an A?
Either they will or they won't.
They could buy you the car, and they might not. The promise didn't say anything about that. Now, we have terms for this. The if part's called the hypothesis, and the then part's called the conclusion. So in my promise about the calculus class, if you get an A in this class as the hypothesis, then I'll buy you a car as a conclusion. Okay? Call that my promise. Okay? Well, in my promise, if the hypothesis is true, you get the A, then I have to buy you the car. The conclusion is going to be true. But if I don't, if you don't get an A, if the hypothesis is false, then the promise doesn't exist. The promise doesn't say anything. I might buy you the car, so the conclusion could hold, or I might not. Now, that's what Zach was asking. He says, isn't it possible for a discontinuous function to have a max and min? It is absolutely possible. So if we had an example, let's first look at what this is saying. If I've got a closed interval, that function right there has both a lowest point and a highest point. Now, when we did optimization problems, we talked about where to find them, right? Where do you look for max and mins? Endpoints, derivative of 0, derivative undefined, right? So now that would be another good question for the quiz on Tuesday, by the way. Where do you look for max and min values, right, for a function, right? Well, we look at endpoints, we look where the derivative is undefined, we look where the derivative is 0, right? Those are the kind of questions I'm looking at for this Tuesday quiz. The ideas behind what we've been doing, okay? So we were concerned with where to find the max and mins, but this is just saying, hey, they exist. They're guaranteed to exist. Now, let's look at Zach's situation. Now, what's it make for a function to be not continuous? A break, or a hole, a jump, a gap, something like that. Now, sharp point's okay. Basically, it's if you have to lift your pencil kind of thing. A sharp point would be okay, like absolute value, that's continuous, right? That's not differentiable. The derivative doesn't exist, but that's for tomorrow. Okay, for continuous, it just has to be no holes, no breaks, no gaps, no jumps, that kind of thing. So if I took this picture, if I took this picture right here and changed it to this, now is that continuous? That function is, that's right. Yeah, I don't like saying we have to lift your pencil because you wouldn't have to lift your pencil and draw around the hole. So that's probably not the best way to describe it. But yeah, that's not the best way to describe it. So no holes, no gaps, no breaks, no jumps, that kind of stuff. Even if you put another point right here, doesn't matter. That's still not continuous. Now, does it have a max and a min? It still has a max over here, and it still has a min here. So again, this is really important because this is what your homework questions are going to be like today. They'll give you a function like that and they'll say, does the conclusion of the extreme value theorem hold here? In other words, you didn't get the A, but did your parents still buy you the car? That's what the question is. The function's not continuous. So this extreme value theorem doesn't promise anything, right? This only promises you if it's continuous on a closed interval, then you'll have a max or min. It's not continuous, so that doesn't guarantee us anything. But the conclusion part still could be true. You might still get the car. Is there a max and min? Absolutely. Now, let's change it just a little bit. Now, is there a max? There's clearly a min value. Is there a highest value? What's the point right before that? If this is 3, tell me the point right before 3. 2.99999. What about another 9? You can't have an infinite number of 9s because that is 3. What's 2.9 repeating? 2.9 repeating is 3. Right? 0.9 repeating is, right? 0.3 repeating is what? 3 9ths? 0.4 repeating is 4 9ths. 0.5 repeating is 5 9ths, right? You guys have done this before, haven't you? You haven't? 0.3 repeating is 1/3, right? That's 3 ninths. 0.4 repeating is 4 ninths. 0.5 repeating is 5 ninths. 0.6 repeating is 6 ninths, which is 2/3. 0.7 repeating is 7 ninths. 0.8 repeating is 8 ninths. 0.9 repeating is 9 ninths. It's 1. 2.9 repeating is 3. They're the same thing. You didn't know that? Never heard that? So anyway, what is the number right before 3? There is no number right before 3. So there is not a max. There is not a max in this one. Now, but again, why does that not break the promise? It's not only is it not continuous, but now it's not even a closed interval. Right? So actually both of the conditions we said are false. So again, it doesn't violate that promise, it doesn't violate the theorem. Okay? Now some of the questions are worded differently. One question might say, here's the situation. What does that say about the extreme value theorem? Well, you'd say it doesn't say anything about the extreme value theorem because the conditions are not upheld. So therefore the extreme value theorem doesn't say anything. Doesn't promise anything.
So it always has to be brackets, it can't just be parentheses?
That's right. It's got to be the square brackets. It's got to be closed interval. Matter of fact, most time when you word this, you don't even use the word closed interval. You just say AB with the closed brackets, which means closed interval. But I put them both in there just to emphasize.
Could you say there's a max at the top of that one?
It's a local max, but a max, oops, we mean absolute max. So we mean a highest point and a lowest point.
So what if that was like the highest one?
It could have been. Right. Now, again, it's possible, we gave the example a minute ago. If I would have stopped this point right here, okay, now, does this function have both a max and a min? Does the conclusion to the extreme value theorem still hold? Yes. Even though this is not continuous, there's still a min here and there's a max there. But again, don't confuse what we're saying here. This is a promise that can't be broken. Okay? We're never gonna. If they ask you, well, does this violate the extreme value theorem? Well, your answer better be no. We can't violate the extreme value theorem. It's proven to be true. Okay? But when they ask you these questions about does the conclusion hold for the extreme value theorem, you could get yes or no depending on if the conditions here, if the hypothesis is false, if the hypothesis is, if it's not continuous or it's not a closed interval, then the conclusion could be true or it might not be true. Right? You didn't get the A, you might get the car, you might not get the car. Okay? But if you got the A, you got to get the car. I mean, that's the deal. Okay? So anyway, you'll see as we get into those questions. All right, let's go to the second theorem that you're going to have. We're going to do 2 today, we'll do 1 tomorrow. The second one is this. The intermediate value theorem. Or your book will call the IVT. Okay? Now this one, I want to word a little bit differently, again, than the book does. I'm going to word it somewhat like what we see here. If F is a continuous function over a closed interval AB, so that's exactly the same. Then for any K between F of A and F of B, I'm going to underline F of A and F of B there, that's important. There exists a C in the interval AB. Now I used open interval there on AB because we want C to be in between. We don't want C to be at an endpoint. Okay, we want it to be in between A and B. There exists a C in between A and B such that F of C equals K. Now again, as often happens in theorems and in theory, the language sounds very confusing. You really have to break it down, but it's written in such a way to be very exacting. Okay, now we're going to say it in kind of layman's terms here to help us understand it. The problem with saying it in kind of simpler language is it doesn't really say exactly what you mean for it. You know, you kind of intuitively understand what you're saying, but you may miss some of the finer points, and that's why it has to be written this way. So that sounds very confusing when you first hear it. Okay? First part's easy, the conditions are easy, but then what are we saying? For any k between f of a and f of b. Now let's think about this. What's f of a mean? It's the y value at the starting point, at the left endpoint A. And f of b is the ending y value. So in this picture, it would be the two big black dots. F of A and F of B. Now I underlined that because this is the most common mistake people make with the intermediate value theorem. People think we're talking about between the highs and the lows of the graph, the max and the min of the graph. This doesn't have anything to do with max and min. Extreme value theorem does, not intermediate. The word extreme value makes you think about max and min, the extremes. Intermediate is more like in between. Intermediate value is like between values. It's between the endpoints, not between the highs and the lows. Very important distinction. All right, so start out here. There's f of A, there's f of B, and in green are all the stuff between f of A and f of B. And k is just some value in between there. It says for any k between them. Then the last part says there exists a c, an input, an x value. There exists an x value such that the output at that x value equals k. And remember, k can be any value in between them. Let me tell you what this is in layman's terms. In layman's terms, this says that if you have a continuous function, meaning no holes or gaps or breaks, and it's a closed interval because we need our starting point and our ending point. If I start here and I end here, I have to go through all of the y values between here and here. That's what it's saying. Now, is that kind of common sense? Right? If I start in Kearney and end in Grand Island, I had to have hit all the points in between Kearney and Grand Island. If I was, let's say we were on Highway 30. Right? I have to hit all the points in between Kearney and Grand Island. Unless I beam myself from Gibbon to Wood River. But if I beam myself from Gibbon to Wood River, what happens? It's not a continuous function at that point. Right? There's a gap. There's a break. Okay? Now listen. Listen. Why is, what kind of a situation, why is that important? It seems pretty obvious. Okay? Listen up here a second now. Why is this important? Well, one mathematical reason where this would be important would be we use it in finding roots, like we were talking about Newton's method. And one of the, if you really had to rely on Newton's method to find roots, okay, and one of the things that I think is, I don't know this for sure, but I think is probably at some point programmed into your calculator, because when you do a solve, if it's doing a Newton's method routine, it's got to have a starting point, a guess somewhere. How does it know where to guess? Well, probably what it does is looks at the various values as it's graphing, as it does looks at the graph or looks at the various values. If I have 2 and 4 right here on a particular function, I'm looking at some values, and I know that 2 has this output, and I know that 4 has this output, and I'm looking for a root. What do I know? Why does there have to be a root in between here? Isn't that the intermediate value theorem? The intermediate value theorem says if I know I've got this point, and I know I've got this point, if this is a continuous function, it has to cross the x-axis somewhere because it has to hit all the values between here and here. That's what the intermediate value theorem is saying. Now, it might hit it more than once. There might be more than one root in there. But the calculator program would probably say, hey, if I got a positive here and a negative here, I'm going to look in the middle, say 3, and make that my guess. And then go through the Newton's method. So the intermediate value theorem would be useful right there in that situation. If it's a continuous function. Now, if it's not continuous, it might jump over the x-axis. It might not hit the x-axis. And that's where you get those warnings on your calculator. More solutions may exist, or those kind of things. Okay? If it detects those kind of situations. All right? But if you know, and this is, again, the title of this section is Why Continuity Matters. If you know a function's continuous, you get this guarantee. All right? But again, it's not between the highs and the lows. We're not saying, now you might look at this and say, but wait a minute. If it's a continuous function, then you know it's going to hit not just these green y values, you know it's going to hit all these too. That's right. But the difficulty there is then you'd actually have to find the max and the min of the function before you could then say that. The endpoints are very easy to find. If I say, hey, I got this function from 2 to 4, it's very easy to find f of 2 and f of 4. All right? For example, let's go to Kearney to Grand Island example. This is Kearney, this is Grand Island. Started in Kearney, I ended in Grand Island. I know I had to hit all the points in between Kearney and Grand Island, but where did I go right here?
Lincoln.
Lincoln, right? I went from Kearney to Lincoln and back to Gibbon and then back to York and then I ended up in Grand Island. Okay? That's north and south. I don't know, maybe that's confusing. Bottom line is I hit a lot of points other than just from Kearney to Grand Island. But the bottom line is I know I was in Kearney and I know I ended in Grand Island. I had to have hit all the points in between. I might have hit some others. But we know for sure we hit the ones from Kearney to Grand Island. Okay. So, you're going to get a lot of questions in the homework that are going to say, does this contradict the intermediate value theorem? Or does the conclusion hold for the intermediate value theorem? Well, that means does it hit all the points? That kind of thing. Okay, here's going to be your homework. Let's turn and let's just do one together here just so you get the hang of it. Page 279. Look at page 279. Now on your homework sheet, it gives you the assignment here, which is 4.8. Okay, everybody, let's get your books open. Let's look at page 279. Come on now. Page 279, you got the homework sheet there. It says we're going to do number 1, number 2, 7 through 16, 18, 22 through 25. Now, like I said, 35 minutes here, you can probably get a lot of that done. Let's take a look at number 7. Okay? Now, look at those two graphs. Look at those two graphs on page 279. Now, what strikes you about them right away? They're not continuous. Clearly not continuous. So therefore, that means you didn't get the A. Right? You didn't get the A. But you still could get the car. Right? Still could. It's okay. You might still get the car. So, read number 7. Read number 7.
Give me $1 million and go look at you.
Okay, what do you think? Why no?
I say yeah.
I see you. Yeah.
If is the endpoint at 2?
Yeah.
Like the y value.
This is the key. Now this is the intermediate value theorem. The intermediate value theorem says it has to hit all those y values, right? It has to hit all what y values?
Between and end.
That's the thing that I was saying earlier that everybody makes a mistake on. A lot of people would look at number 7 and they'd say, hey, it never hits those y values in between 1 and 2. The y values between 1 and 2. Do you see that? There are not any y values between 1 and 2. And so they say, oh, well, that's no good. But what's wrong with that reasoning? What's wrong with that reasoning? It's not about max and min. It's not about from the low point to the high point. Remember, that's what I was saying on this picture. It's about from end point to end point. What's the beginning point of f? The beginning y value. The beginning y value is -2, right? What's the ending y value? 1, right? F of negative, see, it needs to be f of a and f of b. We need f of -4, which is -2, and we need f of 4, which is 1. That single dot that's up there. Does this hit all the y values from -2 up to 1? I think it does. There's a couple places where there's holes, but there's other dots and other parts that fill it in. So this function f hits every y value from -2 to 1, which is what the intermediate value conclusion holds. But again, it wouldn't have had to, right? It wouldn't have had to. It's just because it's clearly not continuous, so this theorem is really out the window. But what they asked there is, does the conclusion hold? Does it hit all the y values? And it does. If you took away that one dot that's over there at 2, -1, that dot, right, that's at 2, -1, if you took that dot away, then this would be null. Because it would never have a y value of -1. But since that dot's there, it does. Okay, that's the kind of stuff you're being asked. All right, rest of the time is yours to work. Like I said, the goal here would be to get done with this in class, so your out of class time could be to get going on that third packet. And if you're planning to get together with people tonight for the take home, that's fine too. But let's get the book assignment